This PowerPoint presentation covers buffer calculations from section 14.6 of our textbook. This second video in the series for this section will walk through the calculations of buffer pH before and after addition of acid or base. Let's first review some problem-solving strategies that we mentioned in the last video. Remember that buffers are solutions that contain large concentrations of weak acids and bases. So we're going to need to use equilibrium concepts and Ka and Kb values to solve these problems. When dealing with a buffer problem, you first want to write down all the major species that are present. Next, you'll look for any reactions that go to completion. For example, due to the presence of a strong acid or base. You'll deal with these reactions first using stoichiometry. Next, you'll solve any relevant equilibria. In many buffer problems, we have to watch out for volume changes. If there's a volume change in the problem, we'll probably want to do the stoichiometry calculations in moles rather than concentrations. And finally, we saw in the last video that there's a useful equation called the Henderson-Hasselbalch equation that helps us calculate the pH of a buffer. This equation states that the pH of a buffer will be equal to the pKa of the acid component of the buffer plus the log of the ratio of the concentration of the weak base component to the weak acid component. Let's look at this first example. We're asked to calculate the pH of a buffer system that contains 0.3 molar ammonia and 0.36 molar ammonium chloride. If we start by drawing a picture of our system, we have a buffer and it contains ammonia and ammonium. Let's list our major species. We have ammonia and we have the ammonium ion from the ammonium chloride. Ammonia is going to be our weak base. Ammonium is our weak acid. And these are a conjugate pair, so this is our buffer system. In this problem, we're not adding any strong acid or base, so we won't have to worry about that step. To calculate the pH of a buffer, a straightforward buffer, we can use the Henderson-Hasselbalch equation. We already know the concentrations of our weak acid and weak base, so we just need to find the pKa value. If we look at our reference table, we see that the pKa of the ammonium ion is 9.24. So we can plug that in. And plug in our concentration values. The ammonia was 0.3 molar. The ammonium ion was 0.36 molar. And putting this into our calculator, we get a pH value of our buffer of 9.16. Question B asks, what is the pH after the addition of 20 milliliters of 0.050 molar sodium hydroxide to 80 milliliters of our buffer solution? Again, I'm going to start by drawing a picture. We have 80 milliliters of our buffer, which contains ammonia and ammonium. The concentration of the ammonia in our original buffer was 0.3 molar, and the concentration of the ammonium ions was 0.36 molar. To this solution, we're going to add 20 milliliters of 0.05 molar sodium hydroxide. So again, let's list our major species. From the buffer, we have ammonia and ammonium. And we also have the added hydroxide from the sodium hydroxide that we're adding. Are there any reactions that will go to completion? Hydroxide is a strong base and will react with any acids that are present. The acid that we have in the buffer is the ammonium ion. So we're going to be looking at the reaction of hydroxide ions with ammonium ions to form ammonia and water. This is a reaction that's going to go to completion because of the strong base hydroxide. So we're going to deal with this reaction in terms of stoichiometry. Also, in this problem, we do have a volume change to worry about. We're starting with 80 milliliters of the buffer and adding 20 milliliters of a sodium hydroxide solution. So we'll deal with this stoichiometry in terms of moles. So I'm going to set up a stoichiometry table. So the first thing that we need to do is figure out the moles of hydroxide, ammonium, and ammonia that we start off with. Recall from the definition of molarity that molarity is equal to moles over volume. Rearranging this, we see that moles will be equal to molarity times volume. So in terms of the hydroxide, we had a 0.05 molar solution of sodium hydroxide, and we had 20 milliliters of this. So we're going to be adding 0.02 liters of the sodium hydroxide solution. And when we multiply this out, we see that this is 0.001 moles of sodium hydroxide. And because of the 1-to-1 ratio, it's 0.001 moles of hydroxide. What about the ammonium ion? Well, it started at It started at 0.36 molar. And this 0.036 molar was in 80 milliliters of solution. Multiplying that out, we find that we start off with 0.0288 moles of the ammonium ion in our buffer solution. The ammonia was 0.3 molar. Again, that was a solution that was 80 milliliters or 0.08 liters. So we're starting off with 0.024 moles of ammonia. Let's go ahead and write these in to our stoichiometry table. For our stoichiometry row, we can use X's. Our hydroxide is our limiting reagent. The reaction's going forward, so we'll have minus X's for our reactants and plus X for our product. Since hydroxide is our limiting reagent, we know that the final amount of hydroxide should go to 0, which tells us that our value of X is 0.001. So when we subtract 0.001 from 0.0288, we get 0.0278. And when we add 0.001 to 0.024, we get 0.025. I'm going to go ahead and move to the next slide to give us some and remind us where we are at the moment. We had just finished our stoichiometry calculation. We had neutralized all of the added hydroxide. We had 0.0278 moles of ammonium left, and we now have 0.025 moles of ammonia. So now we have a solution that has large concentrations of a weak acid and its conjugate base. We have just a buffer. We can use the Henderson-Hasselbalch equation. The pKa is still 9.24. So to finish this off, we need to put in the concentrations of ammonia and ammonium. Concentration of ammonia is going to be the 0.025 moles divided by the new volume of the solution. Since we had 80 milliliters of buffer and we added 20 milliliters of sodium hydroxide, our new volume is 100 milliliters or 0.100 liters. In terms of the concentration of the ammonium ion, we have 0.0278 moles. Also divided by the total volume of solution of 0.1 liters. Plugging all of this in to our calculator, we get a value of pH is equal to 9.19. Let's compare this to our original pH. Of 9.16. Notice that the pH of the buffer did increase when we added sodium hydroxide. but not by very much. The change in the pH is 0.03 pH units. In part C, we're going to be adding acid to our buffer rather than base. Again, let's draw a picture. This time we have 100 milliliters of our buffer, which remember contains ammonia and ammonium. And this time we're adding 10 milliliters of a 0.1 molar HCl solution. Our major species from the buffer are ammonia and ammonium. And we're adding HCl to that. Do we have any reactions that will go to completion? Yes, we have a strong acid, HCl, present. That's going to react with our weak base in the buffer. So we're going to be looking at the reaction of H plus from the HCl. Chloride is a spectator ion, so we can leave it out. The weak base is ammonia, and this will form the ammonium ion. Again, we're going to make a stoichiometry table. And again, we'll need to find the initial the initial moles of all of our species. For the H plus, we started with 0.1 molar, and we're adding 10 milliliters, or 0.01 liters. So we're adding 0.001 moles of H plus. We had 0.3 molar ammonia. We had 100 milliliters of that solution, or 0.1 liters. So we're starting off with 0.03 moles of ammonia. For the ammonium, we had 0.36 molar, again 100 milliliters of that. So 0.036 moles of the ammonium ion. We can go ahead and put these into our stoichiometry table. We see that this reaction goes to completion. Our stoichiometry rho minus x plus x. Again, this time our limiting reactant is going to be a hydronium ion, so we expect that to get completely neutralized by the buffer. So our x value is 0.001. Leaving us 0.029 moles of ammonia and creating 0.037 moles of the ammonium ion. Now that we've neutralized all of the added acid, we're left with a solution containing ammonia and ammonium. This, of course, is a buffer, so we can use the Henderson-Hasselbalch equation to find the pH of the buffer. The pKa value is 9.24. The concentration of A-, which is our NH3, is 0.03 moles of NH3 divided by the new volume, which is 0.11 liters. And our new concentration, whoops, apologize for that. Our new concentration of ammonia, of course, is 0.029 moles of ammonia divided by the new volume, 0.11 liters. And our concentration of ammonium is 0.037 moles divided by the new volume. And plugging that all in, we get a value of 9.13. And again, let's compare that to our original pH. Of 9.16. When we added the HCl, the pH did drop from 9.16 to 9.13. But again, the change is pretty small. For comparison, let's calculate the pH of a solution made by adding the same 10 milliliters of 0.1 molar HCl, but instead of adding it to 100 milliliters of buffer, let's add it to 100 milliliters of water. We've already seen that this amount of HCl is 0.001 moles of H+. When we add that H+ to the water, there's nothing for it to react with, so it stays as H+. So to find the pH of the solution, we need to find the concentration of H+, which is going to be our 0.001 moles, divided by the total volume, which is 0.11 liters, which gives us a concentration of 9.09 times 10 to the minus 3 molar. Plugging that into the pH equation gives us a pH value of 2.04. The pH of water is 7. So adding 10 milliliters of this 0.1 molar HCl took the pH from 7 all the way down to 2.04. That's a change in pH of almost 5 units. Whereas in the previous example, when we added that to the buffer, we got a change of only 0.03 units.